Hello physics students. Today we're going to be learning about multi-body accelerations. And what I mean is systems where it's not just one object but maybe two or three or even four objects, multiple objects in one system accelerating. And so we're going to analyze these systems with Newton's laws, and we're going to look at two examples. One, like a train pulling train cars. That's example one. And then we're going to analyze just conceptually a situation where two people are playing like a tug of war. Now let me just give you a warning that this example, the first one, is probably the hardest calculation that we're going to be doing in this Newton's Law unit. So just be prepared for a pretty long and tedious calculation. But I'll try my best to point out all the difficult spots and sort of guide you through it best I can. So here's the situation. We've got a little toy locomotive here. It's a little dune buggy that we did experiment with earlier. And here are the two cars. Now, the way a train, like this dune buggy, it's like a locomotive, the way it moves forward is through Newton's third law. We studied this, that what it does is the wheels will push the surface below backwards so that the surface will push the train locomotive forward. And so we'll see that these wheels, you see how they're pushing the surface backwards, and then the surface pushes forward. And so what you can see is that when this car accelerates forward, it then causes this string to tighten, and it pulls the second car or the first train car forward. And then in the process, when this starts moving forward, it tightens up the second cord over here, which then pulls this little caboose forward. So that's what we're analyzing. And here's the situation stated out in words. Okay, so let me see, is this track in the way? I don't think so. So let me step aside, give you a chance to jot this down. Okay, so 2 kilogram toy car pushes back on the table with 15 newtons, and then of course that launches it forward. And then we've got a 1.5 kilogram box and a 0.5 kilogram box. The coefficient of friction, because these slide across the table, the coefficient of friction is 0.1, so it's not on the reference table. I'm giving it to you, and we're going to determine the acceleration of the system. Now with all Newton's laws problems, what you have to do is you have to draw a force diagram. So that's what I'm going to do here, and this is going to get complicated right away, so just a warning. So what I want you to do is start off with 3 dots very far apart, because there's going to be arrows all over the place going sideways. If you draw these too close together, the arrows are going to run on top of each other, and then it's going to get even more confusing, impossible to decipher. 3 dots. So this is the locomotive, the toy car. And I figured out that it has a gravity force because the Earth always pulls down, right? No holiday here. It just pulls this down into the surface below. And the number of newtons that it pulls down, I could do 2 kilograms times 9.8. That's the Earth's pull. Now, the track or the surface it's on supports it from falling. So that we call a normal force equal to the gravity. This is the 1.5 kilograms times 9.8. That's the Earth pulling down, and then the track pushing up with the same amount as a normal force. This is 0.5 kilograms times 9.8. F equals mg, right? That's the gravity, the Earth pulling down, and then the track supporting it with 4.9 newtons. So those are all the vertical forces. That's why nothing falls down, because it's held up by the track. Now, the horizontal forces. Here comes the tricky part. So the first force is the toy car pushing the surface below back with 15 newtons. So that you don't even have to draw. I'm just drawing it on the back to remind you. Car pushes table back, table pushes car forward. So there's that forward force driving the whole system forward. So let me just erase this so we don't get even more confused with more forces. So as I said, what happens is that first car accelerates forward and tightens up the slack and starts pulling this second car. So what we then label, is we call that a new force. And what I'm going to do is I'm going to call that T for tension. And we're going to find out that it's less than 15 newtons. So see, I'm going to draw it like this, maybe a little bit shorter so it doesn't run in. So like this. I don't know how many newtons that is. So what I'm going to have to do is leave it as an unknown. And what I'm going to do is call it T1. Maybe it's like 10 newtons. I don't know. I'm going to find it. Now, Newton's third law still applies here. Let's call this A. A pulls B forward. B pulls A right back with the same number of newtons. So there's the number of newtons right there. The same amount in the backwards direction, T1. Again, I don't know what it is. I'm just going to label it as a variable. Now, that ensures that this car starts accelerating forward, right? So this starts pulling, this accelerates, and then what will eventually happen is it'll tighten this cord up and start accelerating this one. So now we have on this one, the cord tightened up, and we have a forward number of newtons. We don't know what that number of newtons is. So now I'm going to call that tension 2. Maybe it's 5 or 3. I don't know. I got to calculate it. Okay? So Newton's third law still applies. If B pulls C forward, C pulls B right back, right? So this number of newtons, if it's 4 newtons, then there's 4 in the backwards direction here. So let's call that T2. And now these two boxes are sliding across the table, so there is friction of the rubbing here. So I've got to add the friction forces. So here's one force of friction. Maybe I'll call that force of friction on, well, I could say like B, right, on object B. And this one is a different force of friction. There. All the forces. Complicated enough yet, right? I told you it's a complicated calculation. So, now we need to determine the net force to determine the acceleration. We don't know what these tensions are, but we could calculate these because we have a formula for the force of friction. It's coefficient times normal force. In other words, the coefficient was given as 0.1, so I'll put that in. And the normal force was 4.9 newtons. And so when I multiply that out, I get 0.49 newtons. Okay? And I could calculate this force of friction also. Coefficient 0.1 times the normal force of 14.7. And when I multiply that out, I get 1.47 newtons. Okay, so 1.47 and 0.49 newtons. Okay. Now that we're done with the force diagram, I'm going to pause and give you a chance to jot that down. Okay, so now when we know all the forces, we got the force diagram, time to move on to Newton's second law. Normally on the reference table and in all my problems, I always write A equals F net over M. But it turns out that in this case, it's simpler and easier to solve if you instead write Newton's second law as MA equals F net. Same equation, right? I just moved the M over with the A. So let me begin with this object. Its mass is 2 kilograms. Now, because this problem is so complicated, I'm going to leave the units off. Otherwise, it gets even harder to see the patterns. So just in this case, for this problem, I'm going to leave the units off. A is unknown. Now the F-net. If you look at this picture, you got two forces in the horizontal direction. Think in your mind, what would I plug in for the net force? Maybe not a number, but what do I do with what arrows to determine the net force? Think about that for a second. Hopefully you said, it's this forward force minus this backwards force. In other words, 15 newtons minus T1. But here's the problem. I've got two unknowns in this equation, so I cannot solve for acceleration without knowing what tension is. So, with no other strategy, let me write Newton's second law formula for the second object. So it is ma 1.5 kilograms times unknown acceleration. Now, look at this diagram. See if you could, in your mind or on a scrap paper, jot down what the net force is for this object. Go ahead, give it a shot. What you hopefully said is it's the forward force, T1, minus the backwards forces, which is T2 and this 1.47. This is even worse. This had two equations, this had two unknowns in it. This has three unknowns in it. So let's move on to writing an equation for this object. So it's 0.5 kilograms, so Ma will be 0.5 A. And then the net force on this object. See if you could figure it out. Maybe not as a number, but as an expression. Give it a shot, and I'll let you think about it, and then I'll tell you in a second. Hopefully what you said is it's this forward force minus this backwards force. The forward force is T2, and the backwards force right here is the 0.49 of friction. So, another equation, two unknowns in it. But what we have now is a system of equations with three unknowns and three equations we could actually solve for all the variables. The easiest way to solve this system is to add up all the left sides and add up all the right sides. So what we have here is 2a plus 1.5a plus 0.5a, which is 4a. On this side, we've got 15. But then, look what happens. We've got positive T1 and negative T1. Positive T2, negative T2. So those add to 0. And all that's left are the numbers. And if you evaluate all those, you get 16.96. Oops, 96. And then if you, so you've got, well, let me do it on another line over here. 4a equals 16.96. Divide both sides by 4, and we have the acceleration of the whole system. Okay. Let me create a pause to give you a chance to catch up if you need it. Okay, so pretty difficult. Look at the force diagram, so many things. Forward force, and then Newton's third law, equal forces. Newton's third law, equal forces. If this pulls that forward, this one pulls that one backwards. Same over here. And then we've got the friction forces. And then MA equals F net for the three objects. Forward minus backwards. Forward minus these two back ones. Forward minus the backward. And then you just add them up and you solve for A. Before we finish with this problem, I'm also going to calculate the tensions involved, the forces in these strings, because sometimes we want to know that if we make a train with these strings, well, what if we make strings, we pick strings that are too weak and they snap on us? So you might want to know how strong these need to be to stay together. In other words, we need to solve for these tensions. So we can do that. Erase this diagram. By taking any one of these equations and plugging in the acceleration into the equation. For example, let's call this 1, 2, and 3. So if I take equation 1 and I say 2 times the acceleration of 3.26. Oh, you know what? I could maybe stick in the kilograms here. Why not? Now that we're to this point, it's not going to be as complicated. So on this side, we've got 6.52. Oops. If we add T1 to this side and subtract 6.52 to the other side, we get 8.48 newtons. So there is the tension, the string strength necessary in between the first car and the locomotive. How about back here, tension 2? It would be most convenient to use this equation 3. So we plug back our acceleration into 0.5 kilograms times the acceleration of 3.26. That's going to equal T2 minus 0.49. So this is 1.63, I believe. Add 0.49 to both sides, and we get T2 equaling 2.12. Okay, so there it is. Let me create a little pause to allow you to catch up if you need it. All right, so we get the system, we solve for the acceleration by adding everything up, and then we just plug in acceleration here, and then we can solve for those string forces, those tensions between the cars, okay? Notice the first force, the locomotive had a forward force of 15 newtons. The force between the cars gets progressively weaker the further you move back through a train system. The biggest force is between the locomotive and the first car, and then it gets weaker, okay? So that is our first example, okay? Now, let's move on to the second example. By the way, the second example is not as complicated in the sense with all these calculations. It's more of a conceptual example. Imagine I've got a tug of war, 2 people, and I'm filming this alone. I don't have any people in class here. But every year I ask a student for a volunteer, to be a volunteer. And then we just kind of do a little mock tug of war. So this is one person, this is another. And we pull, and then someone wins, right? And the question is, how do you win? And students will say, I know how. You pull harder on the rope and you win, right? I'm pulling harder, I'm going to beat the other person. But think about this. Newton's third law. If the winner pulls the loser with 500 newtons, what's the loser pull back with? 500 newtons. So then the winner says, oh, 500, 500, I got to pull harder. Let me pull 600. Loser pulls back 600. It's a law of nature. Isaac Newton said it always happens. It doesn't matter what the circumstance is. One pulls one, the other pulls back the same number of newtons. And so it would seem that there's no way to win a tug of war. People always pull equal, right? Obviously, someone wins. And the question is, how does that happen if people pull equally all the time? There's a piece of the picture you're missing right now. You're doing something else besides pulling on the rope. Do you know what it is? I'll give you a minute to think about it. Think about what else do you do besides pulling on the rope in a tug of war? Maybe you said you push on the ground. If there's no ground, or maybe you're standing on ice, then the people pull and they slide in and they crash together. So nobody wins. You both come together in the middle without traction on the ground. That's the piece that's missing. So, to speed things up and make this video a little bit more efficient, I have prepared a diagram. This is a tug-of-war competition between The Rock. Everybody, well, maybe you know The Rock. I don't know. Movie star, big muscular guy. He plays in a lot of action films. And he's up against Mark Wahlberg, also another muscular guy. He plays in a lot of action, tough guy films, plays boxers and stuff. So they're doing a tug-of-war. And here we are. Action is The Rock pulling Wahlberg with 500 newtons. The reaction, he pulls right back. That's not how you win, right? Pulling more. So here are these forces labeled out. F action is The Rock pulls Wahlberg. Why did I put a minus sign? I'm just going to say left is minus. So that's to the left, 500 newtons. The reaction, Wahlberg pulls The Rock with 500 newtons in the positive direction. But here's what they're also doing. The Rock is pushing forward on the ground while he's trying to go this way, right? So he kicks the ground like that. There. The action, The Rock pushes the ground plus to the right, 600 newtons. And what's the reaction to that? You take the sentence and you flip it around, and now the ground pushes The Rock backwards with 600 newtons. And then Wahlberg, he's not there passive, he's fighting too. He's going to push the ground forward too. So he's over here, and he's trying to kick the ground that way, right? So he's pushing, 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 right? So he's pushing the 400 this way. That's his action. So action number 3 is Wahlberg pushes the ground to the left with 400. That's the minus sign. Reaction, the ground pushes Wahlberg back in the positive direction with 400. So this is the tug of war. Now, who wins? Well, if you look at The Rock, and you look at the forces on him, forget about this. This is on the ground. So there are the forces on The Rock. He's got 600 to the left and 500 to the right. So The Rock has 100 newtons F net. Well, let me write that a little neater. And I guess I said left is negative. So you negative 100 newtons is his net force. And then you look at Wahlberg, Mark Wahlberg, and look at him. Forget about this. This is on the ground. Forget about what's happening in The Rock. And when you look at Wahlberg, he's got 500 to the left and only 400 to the right. So he also has a net force of 100 newtons to the left. So his F net is also negative 100 newtons. So they're both going to accelerate. And if they both have a net force this way, which way do they accelerate? This way. In other words, The Rock wins. Okay? because he accelerates backwards, right, and pulls Wahlberg forward. So who wins a tug of war? Not who pulls harder on the rope. Who pushes harder on the ground to get a reaction to get them to go backwards? Okay, interesting. So let me step aside and give you a chance to copy this down. All right, I hope you enjoyed today. I think if you did enjoy anything about today, I'm going to guess it's this one. It's a little easier than the first problem, very tedious and difficult. So multi-body accelerations. If you have to calculate the acceleration, you have to make a force diagram with all the forces with Newton's third law, action-reaction between the objects, and then use Newton's second law, ma equals F net, make a system of equations for every object as an equation. Add them up, solve for acceleration, okay? Or something a little more conceptual, tug of war, always action-reaction existing between any two objects interacting. Whichever one has the net force in the proper direction wins the tug of war. So, I had fun. Again, I hope you had fun. I'll see you in the next physics video.